This is how liquid metal gets made, and making it comes with a lot of disclaimers.
In theory, it can get warm, it produces hydrogen, it can explode. You should not breathe it in.
Yeah.
Like that could really be dangerous. It's so small that you would not get it back out of your lung. That is copper nanopowder. And that is quite interesting in a term of that if you expose it to air, it can self-ignite.
Cool.
Yeah,
Can we try it?
No?
Liquid metal is one of the highest performing thermal interfaces for electronics. Although it's commonly made out of gallium and indium, it might as well be liquid gold instead.
If it's 1 kilogram of the liquid metal, translate this into 1,000 1-gram syringes that are then being sold for end customer price maybe $7, $8. Right. So that means basically one of those bottles could be 8,000 US dollar of value.
Right. Oh my God, that's heavy. That's deceptively heavy because it's only up to here, right?
It's crazy, right?
Today we're at the Thermal Grizzly factory in Germany, run by this guy, CEO and mad scientist Roman, aka Der8auer.
The gallium oxide will turn into gallium oxyhydroxide.
Okay.
And that is the big problem. The gallium oxyhydroxide.
Yeah, we don't like that. I try to avoid it every day.
Don't we know it, yeah? This
highly specialized thermal interface factory is capable of producing 5,000 to 10,000 syringes of liquid metal per day using this simple, efficient machine and a lot of finely tuned chemical processes.
Just checking that it's the right amount of indium.
So then he's removing some just to get precision.
Yeah. It's kind of like a miniature injection molding machine to some degree. If you film in, you will see that there's a lot of, I would say, nasty looking stuff on the top. That is mainly gallium oxide, which is fine. It protects the liquid metal underneath, but we have to get rid of this.
Okay. Last time, we showed Thermal Grizzly's thermal paste manufacturing process at the same facility as part of our Made in Germany series of factory tours. This time, we're back for liquid metal. Bevor es losgeht, dieses Video wird euch präsentiert vom Y70 Touch Infinite. Jetzt erhältlich beim offiziellen Partner alternate.de. Wir haben das Y70 bereits getestet und fanden die Verarbeitungsqualität konkurrenzfähig. Besonders die Materialien des Gehäuses haben überzeugt. Das Gehäuse wird jetzt mit einem individuell gestalteten Touchscreen geliefert, mit dem ihr unter anderem die CPU-Temperatur anzeigen, Spiele spielen und vieles mehr machen könnt. Die Y70 von Heit ist jetzt außerdem in zusätzlichen Farben erhältlich. Mehr Infos findet ihr über den Link in der Videobeschreibung unten. Ich habe seit der Hochschule kein Deutsch mehr gesprochen, also hoffentlich ist das hier nicht total Käse mit Soße. Siwan Kaitinda Don, Buhaise. Und jetzt zurück zum Video und danke. Height und alternate.de.
This room is, we basically split the company in two fields. We split it into mechanical and chemical.
Okay.
And this is like our chemical playground.
This is cool, yeah.
So that's where you will see paste and liquid metal being made. That is the liquid metal area right here.
Let's walk around, you can show me stuff.
Okay. This is the entire liquid metal area. It's pretty simple and clean, I would say. So for example, this is an oven where we induction melt the stuff, like the gallium, indium, tin stuff. And then we have to purify it, we have to filter it. And that is done here. And we have to, for example, also use some inert gas to protect it from oxidation. So that is, very important. And that's also the reason for this sticky mat on the floor. Liquid metal, if you ever used it, you drop it on the floor. And especially...
So is it really to stop it just from getting everywhere else?
Yeah.
As opposed to stopping stuff from getting in here?
It's like when people walk in and,
trace
walk
liquid,
out and then you can find it everywhere. It's just the hidden raw material room. Anything that belongs to liquid metal manufacturing and also paste manufacturing is in this room.
Is there any special storage requirement for any of this, or you just need shelves and that's it? I mean,
it depends. Some of the materials can be quite dangerous.
Okay.
Depending on how they are stored. All of them, as you can see, they are packed in plastic bags and like multiple layers.
Is it like flammable type stuff, or is it off-gassing? Or?
Yeah. So the stuff on the bottom right is aluminium powder, and aluminium powder is dangerous in a sense that it will form an oxide layer if you just expose it to the air, and it will react with especially the water inside the ambient air. And that is a problem because if you have aluminium and water reacting, and then you have aluminium, oxygen, and then the remaining is hydrogen.
Okay.
And it's also an exothermic reaction, which means that it's getting warm. So in theory, it can get warm, it produces hydrogen, it can explode,
Right.
which we don't want.
Is that why this room is all cinder block?
I mean, that's one of the reasons why this is like a safe.
Secure room. Yeah.
That is copper nanopowder. And that is quite interesting in a term of that if you expose it to air, it can self-ignite.
Cool.
Yeah.
Can we try it?
No. I'm trying not to burn down the factory.
Yeah. How do you interact with it in your process then? Because it sounds like you have to be pretty careful about how you get it into the machine it's going into.
Yes.
So
we have a dedicated box, like a glove box.
I saw that, I think.
Yeah, so that's how we have to handle it. Personally, I'm not that afraid of those theoretical things because it's very unlikely that this is happening. Even with the aluminum powder, you need like a huge amount that it really could become an issue.
Right.
What I think is much more dangerous is the fact that it's tiny powder, like the one on the bottom you can see here. That's 20 nanometer zinc oxide. If you handle it and if there's some dust in the air, you should not breathe it in.
Yeah.
Like that could really be dangerous.
That makes sense.
Like in terms of it's so small that you would not get it back out of your lung.
Right.
So yeah, that's why if we're handling this, we will have to wear a protection, you know. This is the raw material for the liquid metal. So that's what we will start with. This is pure gallium.
Oh, cool.
That's that's the main component for liquid metal making. This is 1 kilogram of indium, and the value of this type of purity is about $400. Today we will make Conductonaut Extreme, so we only need gallium and indium.
Okay.
We'll just grab some of the indium and this gallium.
Okay.
And then what we usually do first is we have to check if it's the correct material, because you know when you get this,
Just to be safe,
you just don't know if it's the right, and also if it's the right purity. Well, everything that we're making, quality matters in terms of that it would have a huge impact on performance or like aging and everything, and that's why we have to check purity of the materials, and that's what Florian is usually doing.
Okay.
The cool thing about this machine is that it's X-ray spectroscopy, but you can do it through other materials. It has to run 3 times, and then you get the result right here, which tells us that it's 99% something indium. Now, this is a little bit off the reality because we're measuring through the
plastic,
through the plastic. It would be more accurate without, but like for checking if this is the right material,
enough.
Yeah, if it's 99%, then we know it's indium. Cool thing about liquid metal is that if you let's say you screwed something up in a mixture, you can always alloy it again, you know?
Right,
So you can heat it up, you can add other stuff to fix it, to have the matching.
If you look at the mixture when you're done, and there must be some level of mathematics and chemistry, I guess, involved to determine what's missing or what needs to be removed or whatever.
We have like a calculation tool where we enter all the stuff. Starts with, I'm not sure what the English term for this is, the bucket. It's like a...
Bucket is an English word. That's a good start. Your English is getting better.
Thanks.
You know the word bucket now.
Kannst du mir so einen Titel geben?
What is it called? Like a crucible.
Okay.
How about that?
Whatever you say, crucifix.
No, that's a different one. I think crucible is the right word. It's my understanding is they're used to just like melt things.
Yeah. So it's made from graphite because graphite has no interaction with either of the materials we use.
Oh, okay.
Yeah. So you can, like, you see how clean this is.
Yeah.
And you can pour gallium indium tin inside, and you can pour it back out. Yeah. Is that the only thing you make that you might melt down? Yeah.
Right now? Okay.
Yeah. It's the main, we experimented with other stuff. There are also something called fields metal, which is made from different metals, but it was never good for us. So. Is
it always worth trying to reclaim it? I mean, as opposed to just saying, we screwed this up, just throw it out?
It depends how bad it went.
Okay.
So there are a lot of things that can go wrong. And for example, if you heat it up too much, or if you forget about the gas supply, then it could be a problem. Like you're maybe introducing too much oxide into the material, and then there's a process of aging. Well, it's not aging, but there's a process of continuous oxidation going on.
Okay.
And then it will just harden over time.
So once again, like Intel.
So yeah.
My goal is to get you in trouble with at least one company at the end of this.
We should just go through the process
Yeah.
and then you see how this is done.
Yeah, let's do it.
Mach einfach mal komplett
Ja,
und ich erkläre währenddessen.
So walk us through what he's doing.
Yeah, we're tracking everything we're doing. So he's preparing the batches. So we will have 1 kilogram roughly of the liquid metal that goes into the bottle, and out of that bottle we will take a small sample that we store for at least 2 years.
What's the storage for? What's the purpose of?
Because we sell a lot into the industry.
Okay.
I would say 80% of what we're producing here goes to other industry partners, and some of them require additional quality steps.
Okay.
We have multiple steps of weighting a single thing, tracking everything down. Better safe than sorry.
And I guess he's got a spreadsheet or software or something.
Yeah, it's like our own Excel sheet.
Is that something we need to not show?
No, it's fine.
Okay.
I can show everything.
Okay.
So the bottle is also quite interesting actually, because it's a dangerous good bottle. Because gallium indium is a dangerous good after it's made.
Okay.
Because gallium is very corrosive towards other metals. So what he's doing now is just getting the raw parts of the gallium first.
Okay.
Yeah, so first is the gallium. The amount of gallium just determines how much of the other materials we need. So it doesn't really matter if he starts like with, I don't know, 900 grams or like 1,000 grams. Now it just matters how much of the indium he has to add.
Okay. And then he uses the calculator tool to figure that out.
Yeah. We always track before and after adding the materials, also to see if something went wrong during the process itself. Yeah.
So what's he checking for? The amount, I guess?
Yeah.
And then he's going to watch the scale while he pours?
Yeah. Just checking that it's the right amount of indium.
So then he's removing some just to get precision?
Yeah.
That is
like there's always going to be a certain tolerance in making this.
Yeah.
And the exact ratio will determine the melting point. But the melting point is actually an interesting part about liquid metal because it's volume dependent. That is something that also, when we started making this, it also blew my mind.
Does it go up as you have more volume or down or what?
It goes up if you have more volume.
Okay.
So that's also the reason why we only make 1 kilogram in this bottle and not more.
As someone who doesn't understand chemistry,
why? It's because any metal alloy has to be super cooled. It's called to melt to solidify. It's the same if you're making iron or steel, for example. If you're mixing different metals into an alloy, it's not a fixed melting point, and you have to have, I think it's called nucleus, where it starts to crystallize.
So you want that?
No, we don't.
You don't want that.
We don't want. We don't want it to
Understood.
crystallize.
I will not make liquid metal. I would be very bad at it.
So that's why
I've already screwed up.
That's where the purity comes into play. So if you have less purity, it will just solidify earlier because you have more like dirt inside that act like as a crystallizer. So he entered the bucket.
Yeah.
Can't remember.
Crucible, I think.
Into the induction oven, and then from the top we add the inert gas. The inert gas is needed to avoid oxidation, or to at least reduce it as far as possible.
So if you didn't use any gas at all, I mean, is it basically just like instant oxidation?
Yeah.
Okay.
It will oxidize anyway, anytime, but the question is how much oxide you will have. Like with this, we just minimize it. There will still be oxide, and we will have to filter it out later with this.
Okay. So what's he doing now?
So switching on the chiller, because the oven itself has to be chilled from the outside to not blow up, or whatever it was to, yeah.
So how long does it take to melt?
A few minutes maybe.
Okay.
That's very quick. The induction oven introduces about 5 kilowatts of heat into the material.
Okay.
And because it's induction, it directly goes into the metal. Florian just said that it takes a maximum of 90 seconds to heat it up. He also has this graphite thing to poke into the material, see if it's liquid, if there's anything that he can stir around.
And then I see he's got, looks like a thermometer as well.
Yeah. Now he will check if the intended temperature was reached. Can't tell you the intended temperature.
That's fine. Can you give me an understanding, I guess, at least, of...
Well, it has to be... We have indium that has a melting point of 157 degrees Celsius. and gallium is about 30. So it has to be above indium. But you also don't want it to be too high, because the higher you go, the quicker the oxidation happens. So you have to balance that off.
Is that the only downside for going too high? Is basically the rate of oxidation?
Yeah.
Okay.
Well, also that it will introduce more time for the process itself.
Right.
That was basically the making of the liquid metal. It's
Cool.
pretty simple and quick to just make the liquid metal itself. Just has to be very controlled, that you're hitting the right temperature, that the purity is correct. And now we have to wait about 2 hours for the material to cool down.
Okay.
We let it cool down at room temperature. We experimented with cooling it down quicker, but that also causes problems.
Same type of problem or different?
Yeah.
So oxidation again?
Oxidation and de-alloying.
Okay.
Yeah. After this is cooled down, we fill it in syringes.
Is there a problem if it sits too long? I mean, if you have a bunch sitting and then you guys leave for holiday break and you come back in a week?
No.
No problem, okay.
When we fill it into the bottle, we do it at the same time when filling the bottle with gas. So it's either, usually we use argon, sometimes we use nitrogen, but argon is usually the way to go. And then inside the bottle, there's nothing happening. Like we have controlled temperature and there's no oxygen for oxidation.
What goes into the selection of the gas, the type of gas?
Mainly the price.
Oh, okay.
Price and availability. We will now filter this and fill it into the storage bottle.
Okay. You mentioned something about the storage bottle earlier.
Yeah.
I don't remember what it was. You said to ask you about it.
You mean,
something special about it.
There are two things. I mean, first of all, the bottle itself is specialized, so we can store and ship liquid metal as a dangerous good in there, even like express freight, which is usually a problem. And what I usually think is interesting, if we translate, if it's 1 kilogram of the liquid metal, translate this into 1,000 1-gram syringes that are then being sold for end customer price maybe $7, $8.
Right.
So that means basically one of those bottles could be $8,000 US dollar of value. Right. Which is obviously not the case, because there's like
all the cost and
the cost and
overhead.
then salary in between and everything.
Yeah.
Florian now double checked the temperature to make sure that it's all cold, as it's supposed to be.
Since it's sat for 7.5 hours.
If you film in, you will see that there's a lot of, I would say, nasty looking stuff on the top. That is mainly gallium oxide, which is fine. It protects the liquid metal underneath, but we have to get rid of this.
Okay. You can see it shimmering from here.
Yeah. And to get this out, we're just filtering the liquid metal. For this, we made our own filtering devices.
Okay.
Because they inject the argon gas into the bottle while we are filtering. So now the argon gas is basically coming out here to just minimize any oxidation.
Okay.
So even if it's now into the filter, like open, then it wouldn't oxidize because of the argon coming in from the bottom and the argon being in the bottle after we close it. The surface tension of the liquid metal is really high, so if it's a new filter like this one, we usually have to move it a little bit to get it going, the flow going. And once it's through one time, like now, it will start to drip down.
Okay, yeah. Kind of just reminds me of a coffee filter in some ways.
Yeah.
Oh my God, that's heavy. That's deceptively heavy, because it's only up to here, right?
It's crazy, right?
Yeah, it's very dense.
Yeah. I mean, you have to think about that. This is 1 kilogram.
Yeah.
Like, and this is a 1 liter bottle.
It's crazy.
Yeah. So if you would fill this, it would be like 6 point something kilogram. That is the machine that we use for getting the liquid metal into the syringe. That was also a big challenge because of just how the material is. Like, it's corrosive. It has very high surface tension, very high density. It's kind of like a miniature injection molding machine to some degree. And what we have here is the reservoir where we have to fill in the liquid metal from the top. And then we have just a mechanism inside that pushes this very controlled into the syringe. There you can see a bunch of liquid metal inside. So what we would now do is we take the liquid metal and the funnel and just pour it into there. I mean, there's still plenty inside, so I skipped that right now.
Okay. What's sort of the rate of this machine? I mean, if you have someone working at their peak efficiency, How many syringes do they fill, in an hour, a day, or whatever?
I will let Florian do it.
Okay.
But it's a couple of thousands a day.
Yeah.
Kannst du einfach ein paar? I think for this type we're selling maybe like 15 to 20,000 per month of this 1 gram Conductonaut Extreme. I would say overall it's about 100,000 syringes per month, especially the first ones. The first ones are always a bit critical when it comes to the filling. So every single one is checked on the scale, and then like this one we see it's below 1 gram.
Yeah.
And then it goes into the yellow bucket.
Okay.
And usually we also have the PC connected to it, and then we can adjust the parameters if needed. It's also 2 steps, which you can't really see. But now it's 1.05 gram. That's exactly where it should be. We have some range, so we don't go below 1 gram, obviously. But sometimes, let's say there might be something out of range that is maybe 1.5 gram.
Okay.
And then the customer is just lucky.
Yeah, right.
Because we won't spend more time. So this one still goes into the yellow bucket.
Okay.
Yeah.
And what did you say happens with them when they go in the yellow bucket?
Once they're enough, once there's maybe like 100 or something, someone manually fixes this.
Okay.
Yeah. I mean, if we notice that it's too many now, like if we say it's 2 or 3 more, then we will have to adjust it with the laptop to just
to spit out more.
Yeah. So 1.3 is fine, but the average is 1.1.
Okay.
So if you take a couple of thousands, the average would be 1.1 gram. And there's anything in between, like 1.0. It can be. I think the highest we had was like 1.7.
Wow. Okay.
Now it's 1.03, where it should be. But for us, it's like the time benefit we have using this machine weights higher than the cost of the material.
I see. It looks like he's pulling the plunger and pushing it again when he gets a new one.
Yeah.
Is that to get rid of air, or?
If you take one of those syringes,
Yeah.
those are actually medical grade syringes. But the thing is, you can try to just pull it initially the first time.
Just pull?
Yeah. And you notice the first pull just takes more force.
Resistance, yeah.
Yeah. And this will impact the distribution.
Right, okay.
So yeah, that's how you put the liquid metal into the syringe in the end.
Cool. And then you said the rate, he can do how many per day?
Easily like 2,000 or 3,000 a day.
Yeah.
And we have 2, so we can, if we just put 2 people there, we can do, I don't know, 5,000 to 10,000 a day.
But then, I guess you're not doing that every single day either.
No,
right?
no.
Okay,
No.
so it's all in batches.
But as you can see, maybe it takes, I don't know, 10, 15 seconds per syringe. It is quite fast.
Yeah.
And essentially, it is exactly the same for any conventional paste.
And while the relatively lean manufacturing process is ongoing, R&D happens just upstairs at the scanning electron microscope.
I told you we're working on stuff to protect copper underneath, well, copper from gallium. And what we were testing here is the effect of the gallium on copper in the vacuum inside the SEM. It's a copper sample, and then liquid metal was applied to it. And this is how it looked zoomed in after, I think, maybe half an hour after applying it.
Okay.
Almost no interaction that happened, almost no oxidation. What you can see here is just the copper looking through, and anything that's above here is
liquid
metal. That is exactly the same position about 2 weeks later.
Oh wow, okay.
Yeah. And you can see definitely how it changed on the surface. And because we know it's stored in the vacuum, can't be oxidation. What happens is that you will have a different composition left on the surface than what you want it to be, right?
Right.
So it's kind of de-alloying, and it's no longer liquid at room temperature because of the gallium forming an alloy down there.
Okay.
And that's what is left. So that's what people see when they're applying liquid metal to copper, and then it looks dried out.
Right.
It is just because of gallium going into the copper, and then you're forming those different alloys, and then what you have left is not the original composition of liquid metal.
Okay. Does it affect performance?
Yeah.
Okay.
The biggest
Because I've seen it, you know, like we've reapplied liquid metal over the years to some machines, and because you can see it. What was never clear to me was, is it purely cosmetic?
No, it's not. The problem is with those intermetallic connections. For example, if you're looking at copper digallium, it's called. So it's one atom of copper, and then there's 2 pieces of gallium.
Okay.
The conductivity is not even half of what copper usually has. And the more you alloy, so the more gallium you add to the copper, the worse it becomes. That's a typical thing for any alloy. If you take 2 pieces of metal and connect them, the conductivity will always be worse than any of the single ones.
Okay.
And the more you mix it, the worse it becomes. It only becomes really bad once you don't have any liquid left. Like here you can see, especially here, there is still liquid stuff. So this would not be too bad, but it will become bad once the oxidation happens. Then you will have gallium oxide forming, which itself is not that bad. But there is a secondary step afterwards, which is called hydrolysis, where hydrogen from the ambient moisture that you have, the water, will interact with gallium oxide.
Okay.
So the gallium oxide will turn into gallium oxyhydroxide.
Okay.
And that is the big problem. The gallium oxyhydroxide.
Yeah, we don't like that.
It's
that's bad.
Yeah, it's really bad.
I hate it. Yeah. I try to avoid it every day.
Don't we know it? Yeah. The big problem is that if you have gallium oxyhydroxide, it will de-alloy the composition. So you will have spots with more gallium and more indium, and that's how it looks dried out.
Okay.
Yeah.
Cool.
And with spots I mean like not like physically like a millimeter, but like a small spot here and a small spot here.
Right.
Yeah.
So then I guess that's what you're working on, trying to engineer a solution to.
Yeah, we've been working on that for a long time now. The first problem was to understand what is going on. Like, what is even the problem? You can't fix it if you don't know the problem, right?
There's a few other quick, cool things we didn't really get time to talk about. One of them we're not going to demo, but that is
It's an argon ion milling cutter.
Okay.
So it uses a triple ion beam source that can cut through material. It's very slow, so it takes for 1 millimeter, it takes like 1 day.
Oh wow! Okay.
It takes a very long time. It's the most precise, and can just cut through material without physically causing defects.
Cool. Yeah. So that's useful for like FA stuff too.
Yeah, for material analysis, looking through chips, cross sections.
And then how about this thing over here, just quickly as well? Because this is all. I mean, you've got.
This is a water cooling station, which is also quite precise. Essentially just a normal D5 pump. We have a Mora from Watercool and a Keyence flow sensor that is touchless. So it's measuring the flow with ultrasonic.
Yeah, we have one of these.
And just some very precise built-in temperature sensors at different locations.
I see the camera taking a shot of what?
That's the control unit underneath it.
Oh, okay.
That's where we can control pump speed and temperature sensors and everything. And on this, we were currently running some temperature cycle testing for a project we're working on regarding a different kind of coatings, because we want to move away from nickel plating.
Cool.
And for aging testing, we just run this and do like 5,000 temperature cycles. And then it's just taking screenshots once in a while. And then we leave open the webcam software that captures this.
Yeah.
And then we just have everything on there.
Cool.
So it's just a workaround to keep it simple.
What do you, for anyone watching this who is, I've started trying to ask this at the end and we can keep it short, but who's interested in getting into any of this kind of line of work? You've shown a lot of different types of things that can be done today. All right, we've looked at chemistry, mechanical, industrial, to some extent engineering. What's your general advice, someone who's interested in this and doesn't know where to start?
The question is, what do you want to achieve and where do you want to go? Like, do you want to work in a field, then it's usually better to specialize in one direction. Let's say you do something like Joe, which is like extremely good at like the CAD work and getting those fittings, for example. Or if you're more into chemistry or physics, then you might want to work on an SEM Like typically if you study physics, then you might get in touch with something like this. From my side, I usually get to work with everything. Like I know most of the stuff, but not as well as the people who are working on this on a daily basis. So yeah, it's typically better to just specialize on one field.
That's also experience though, right? Like that takes time, so.
Yeah, but if you want to get into the, let's say, the PC industry, it is a pretty small world in the end. Like even our company, we're like here on this location, we are about 30 people overall, and that's just for R&D and production. So it's not that big. So it's very competitive as well.
I mean, even the big companies, right? Like ultimately, everyone in the industry knows all the same people for NVIDIA, Intel, AMD. Like
even the other water cooling companies, they're all none of them is like 1,000 people. They're all small. Even if you look at Corsair, for example, the water cooling department is also just a few people. It is a smaller world.
Yeah. And we're gonna go see water cool tomorrow.
Yeah.
Which will be a separate video. So thank you all for watching. Check out Der Bauer's YouTube channel, Der Bauer EN. Or if you speak German, you can go to Der Bauer, not EN.
That's true.
It's auf Deutsch. Subscribe for more. We'll see you all next time. Hallo und willkommen to my channel. Rücksprache mit Intel und anderen Reviewern hatten andere nicht so eine schlechte Performance in diesem Spiel. Das große Problem, I know what that means, hatte ich allerdings mit PUBG und auch hier wieder etwas, das Intel nicht nachvollziehen konnte.
That's pretty much correct. It hurt
Can I say that?
It hurt my feelings when I found out that Intel did not test PUBG.
Is that what that says?
Yep.
It says it's the
größte
Problem.
Yeah, my biggest problem.